Assalamualaikum and a very good evening to Dr. Yakubi and Mr. Han. Today I will be presenting my SIP on RCB modification work due to height clearance shortage at basement car park. The overview of this presentation will be on the introduction, methodology, literature review, results and discussion, sustainability, and conclusion. Introduction includes background of study, problem statement, objective, and scope of work. The methodology includes milestone and Gantt chart, the construction of 2 numbers of basement beam and column on beam, the modification of 23 numbers of level 1 beam, and the project activities. The literature review includes the strength difference of RC beam by post-installation and cast-in-place rebars, and the impact of beam strengthening with CFRP. The results and discussion includes the calculation and explanation on the capacity of non-strengthened and strengthened level 1 beam, the need of beam strengthening, the need of new column on beam and new beam, the final result of basement car park height clearance, and the temporary steel props design. Sustainability will be discussed on the environmental, economic, and social aspects. And finally, the conclusion, where I will relate it with the objective, problem statement, methodology, and results. As for the introduction, I will start off with the background of study. It is believed that a good building design is not just strong, safe, and aesthetic, but also practical and functional. Failure in practical design of a building will give a negative experience for the occupants in utilizing the area. Of all the practicality factors in a building, height clearance is one of them. Beams in a building takes up the most in height clearance of a certain area. This is due to the depth of the beam that is much higher than that of a slab. With the shortage of height clearance due to high beam depth, modification work to reduce the beam depth requires strengthening approach due to the loss of beam capacity. Strengthening of RC beam is believed to be widely applied in the construction industry, mostly due to the aging of the structure. Renovation works for newly constructed RC structures where it requires hacking and reconstruction is considered as a rare case in the construction industry. Methods available such as addition of rebars, steel plates jacketing, externally bonded FRP are widely used depending on the criteria of strengthening approach. The biggest factors of FRP's increasing popularity are due to its high in strength to weight ratio and shorter time of application. Based on my research, FRP for strengthening is proven to be increasing the flexural and shear strength of an RC structure. Various available FRP composites in the market these days are like glass, carbon, aramid, and basalt. Among all these FRP composites, CFRP has the best mechanical properties, but the material for its production is hard to find. These days, CFRP is available in strips, laminates, sheets, and plates. In the case of RC beam strengthening in Sunway International School Subang, the method of externally bonded CFRP sheets is applied. Coming to the problem statement, 23 numbers of level 1 RC beams were constructed with a high depth that has caused the shortage of height clearance in the basement level. The architect intended the basement level to be a car park area. The standard height clearance for an indoor car park as suggested by the architect is 2.4 meters. Certain areas in the basement car park is not complying with this standard height. So Sunway Construction as the main contractor was instructed to modify the depths of the constructed RC beams. For such major RC structures modification work, it is crucial that the original integrity of the structures to be maintained. Critical analysis on the reduced beam depth capacity will be done to prove the success of the design provided by the structural design consultant. The reason of beam strengthening approach in flexural and shear strength, as per design by the consultant, needs to be figured out by this critical analysis. In order to achieve that, research on available articles related to the scope needs to be done. The objective of this beam modification work is to reduce the depth of 23 numbers of existing RC beams that is affecting the height clearance of basement car park without losing its original integrity. Proper construction methodology is crucial to achieve a successful major RC structures modification work. The final height clearance of all affected areas needs to be within the standard indoor car park height clearance, which is advised by the architect to be 2.4 meters minimum. Prior to ensuring the capacity of the modified beams to be higher than the applied loading, critical analysis on the design calculations of these affected structures is required. To support the critical analysis on design calculations made, research on the beam strengthening approach as adopted by the design consultant is required. The scope of work of this beam modification process is the modification of 23 numbers of existing level 1 RC beams, the construction of 2 numbers of level 1 RC column on beams, the construction of 2 numbers of basement RC beams. All these structures are required to be modified since they are interrelated in terms of the load transfer and design load capacity. The overall activities include temporary steel props erection, hacking of RC structures, cutting of existing exposed rebars, roughening of existing RC surface, post-drilling into existing RC structures, post-installation of starter bars, or also known as starter bars planting, lapping of new main rebars, bending and welding of existing shear links, formwork closing, concrete pouring and grouting, wrapping of CFRP sheets, and fireproofing by shotcrete method. The date of work commencement started on 20th of September 2021 and it was scheduled to finish on 16th of November 2021. But the actual finish date was on 6th of January 2022. The major delay in this process is due to the construction work conditions. This is the basement and level 1 layout construction drawing where these two pictures on the left shows the affected level 1 RC beams, while the picture on the right shows the new basement beams and column on beams. So coming into the methodology, I will start off with the milestone of the project. Since milestone is more focused on the deadlines of work scopes, the target and actual finish dates of all the work scopes are stated here. The delay of each of these work scopes are due to the unavoidable construction process condition. The work that has contributed to the most of the project delay is on the reconstruction of level 1 beams. The targeted finish date was on 16th of November, but the actual finish date was on 28th of December, which is about 1.5 months of delay. The Gantt chart for all the tasks or activities involved is presented in this figure shown. The tasks are divided into two groups where one is on the basement beam and level 1 column on beam construction works, and another one is on the level 1 beam modification works. Of all the tasks, the one that is taking up the most time is the main bars and shear links installation work of level 1 RC beam, which is almost 2 months of time taken. In order to expedite the construction and modification work processes, the tasks that are applicable to be started simultaneously are done. So for the construction of basement beam and the column on beam, it started with the demarcation of basement slab hacking area, which is 700 millimeters width times 7,000 millimeters length. The demolition of 450 mm thick basement slab was done by a robotic hacking machine and a manual electric breaker, followed by the cutting of exposed existing slab rebars by using oxytorch and 4-inch grinder. When the slab hacking process is done, the excavation of 600 mm soil started. Anti-termite and 50 mm thick lean concrete were done prior to the construction of RC structures in contact with ground. The roughening of concrete surfaces such as the sides of pile cap sides of slab, bottom of level 1 beam, which are in contact with the fresh concrete, is required to ensure a better bonding of concrete to concrete structure. Concurrently, the post-drilling of the existing concrete surfaces are done for the post-installation of rebars. The depth of the post-drilling work is 12 times of the required bar diameter. The post-installation of rebars include the basement beam rebars, which is to be planted on the sides of the pile cap, the basement slab rebars, which is to be planted at the sides of the existing exposed slab rebars, and the column on beam rebars, which is to be planted on the bottom of the level 1 beam. Prior to the post-installation of rebars, chemical adhesive injection of Hilti Heat RE500 V3 into the drill holes is required. This is for a better bond strength of the bars and the surrounding existing concrete structures. Rebars installation process, including 40D of lapping length, begins with the beam, followed by the column on beam and then the slab. Then the inspector of work was invited to verify all the rebars installation. After the successful inspection process, the construction of formwork was started. For the formwork of column on beam, a letterbox opening is required for the concrete grouting process. The beam, slab, and column on beam were cast monolithically with concrete grade of G30. External vibrator was used for the concrete compaction process. The formwork was finally removed after 72 hours of casting time. So these are the pictures of the actual construction process of the basement beam and the level 1 column on beam. Coming into the construction procedure of level 1 beam modification work, it started with the demarcation of beam hacking area. The area is depending on the depth of the beam to be reduced, as per the drawing details provided. Prior to major modification of RC structures where major hacking is required, temporary steel props erection is compulsory to prevent the affected structures from collapsing due to the loss of its capacity. Secondary beams were demolished first, followed by the primary beams. The demolition of beams were done by robotic hacking machine and manual electric breaker. All the exposed existing rebars are cut by using oxytorch and 4-inch grinder. Roughening of concrete surface in contact with the fresh concrete is required for the concrete to concrete bonding. In this case, the adjacent column surfaces in contact with the modified beams are roughened. Concurrently, the post-drilling process into the existing adjacent columns was started for the post-installation of beam rebars. The depth of the post-drilling work is 12 times of the required bar diameter, which is also known as 12D. Then the injection of chemical adhesive into the drill holes for the starter bars planting is done, followed by the rebars installation process that includes 40D of lapping length. After rebars installation process is done, the inspector of work was invited to verify the rebars installation. The construction of formwork with letterbox opening for all beams are required for the concrete grouting process. All beams were cast with a concrete grade of G30. External vibrator was used for concrete compaction. The formwork was finally removed after 72 hours of casting. Prior to the wrapping of CFRP sheets for the strengthening approach, surface preparation process are required where all latents and kinks were removed and the surfaces are ensured to be free from any dust. CFRP CICAREP 301C sheets were cut to the required length according to the respective modified beam depth. Epoxy resin Cicador 330 was applied onto the beam surface with a brush, followed by the wrapping of first layer of CFRP sheets by full wrap, which means the wrapping at the sides and the soffit of the beam. Rubber roller was used to ensure the CFRP sheets are properly stick to the beam surface. The second and third layers of CFRP wrapping requires similar procedure as the first layer, and the final layer of CFRP sheets is coated with a layer of epoxy resin. Silica sand was sprinkled onto the surface while the epoxy resin is still sticky. Then the beam is ready for the next step, which is the fireproofing process after 24 hours. Holding pin was stick to the beam surface with 250 mm spacing center to center, followed by the wire mesh installation. Fire protection mortar Sikacrete 213 FMY was applied with 40 mm thickness by shotcrete method. Finally, the beam surface was manually leveled by using trowel. These are some of the pictures taken by myself during the level 1 beam modification works. The picture on the left is taken during the concrete demolition process. The exposed rebars can still be seen in this picture. The picture on the right is taken after the main bars and links installation process are done. The picture on the left shows the formwork construction process with letterbox opening provided. The picture on the right shows the progress of CFRP sheets wrapping process. The two pictures on the left is taken during the fireproofing process. The holding pins that is placed 250 mm spacing center to center can still be seen in this picture. The picture on the right shows the final result of level 1 beam modification work. So coming into the project activities, throughout my entire involvement in this project, these are the activities that I have been doing from the start of the project until the end. When I first heard about the beam modification process, I immediately went to the basement level to physically see the affected level 1 beams that are causing the height clearance shortage. Then I studied the construction drawings in the site office to get a better understanding of what is required to do to achieve the standard height clearance as stated by the architect, which is 2.4 meters minimum. The general arrangement plan, the beam detail, the general note, the concrete plan, the architectural layout are some of the drawings that I studied. I also read on the work method statement to understand on the construction procedures, which I believe it will help me to understand and acknowledge the overall construction processes. After weeks of my involvement in the project, I started to have questions in my head on the design of the beams. I was wondering whether the modified beams can cater the applied loading. So I wanted to apply my technical skills learned during RC design class to evaluate on the beam capacity. The application of CFRP sheets for the beam strengthening and the capacity of post-installed reinforcement bars are also wondering me, since I have very little knowledge on this area. So I knew that I had to do critical analysis as well as research on articles to answer all the questions I have been asking myself. Then I started to work on my report, where the work of writing everything down is being progressively done, followed by this presentation. As for the research that I have done, in which I consider it as the literature review, these are the two components that I have been working on, which I believe will help support my critical analysis. The strength difference of RC beam by post-installation and cast-in-place rebars. The research paper adopted was the evaluation of bond strength of bonded in or post-install reinforcement by Ahmad, Al-Hamud, and Kunz. The paper is about the experimental tests on the strength of bent and straight cast-in-place rebar and straight post-install rebar. The experiment was carried out by applying lateral compressive force to the faces of the vertical elements by using two hydraulic rams, that is 300 kN capacity each, and placed at around 160 mm from the tip of the two vertical elements. In this experiment, the vertical elements are acting as a beam, while the horizontal element is acting as a column. The picture on the left shows the casting band bars, while the picture on the right shows the casting and post-drill straight bars. As it can be seen on the right is the test results of the experiment. Set 1 is chosen as example for explanation purpose. The casting band bars was able to take 171.69 kN of ultimate load and 29.97 mm of deflection. The casting straight bars was able to take 116.27 of ultimate load and 17.04 mm deflection. The post-installed straight bars was able to take 143.75 kN ultimate load and 33.39 mm deflection. With this result, it is concluded that post-install straight bars using appropriate adhesive mortars develop similar or greater bond strength than that of casting straight bars. However, casting band bars, which is usually adopted in construction, has greater bond strength than that of post-install straight bars. The next literature review is on the impact of beam strengthening with externally bonded CFRP. There are two criteria concerned in this literature review, which is the first one is on the flexural strength and the second one is on the shear strength. The flexural strength is adopted from the research paper by Murad, an experimental study on flexural strengthening of RC beams using CFRP sheets, while the shear strength is adopted from the research paper by Adikari and Mutsuyoshi, behavior of concrete beams strengthened in shear with carbon fiber sheets. Both research papers use a similar approach in the experimental test procedure, which is a simply supported beam and 4-point loading test. So the below picture on the left is the test procedure illustration of flexural strength test by Murad, and on the right is on the shear strength test by Adikari and Mutsuyoshi. The above figure is the test results of flexural strength and the below figure is the test results of shear strength. For the flexural strength, Murad concluded that beam with 45-degree inclined CFRP sheets provided the best performance where the specimen experienced additional deflection limit and flexural strength of 56% and 12% respectively, while the reduction in its ductility of 8%. While for the shear strength, Adikari and Mutsuyoshi concluded that beams with fully U-wrap sheets having vertically aligned fibers provided the most effective strengthening with 119% increase in shear capacity as compared to the control beam without any strengthening. With these research paper results, it can be concluded that externally bonded CFRP provided the most in shear strength capacity of a beam. So coming into the results and discussion, the calculation on the capacity of both non-strengthened and strengthened beam 2B.410 were made. Non-strengthened beam means the beam with the original design before the modification work with 4T25 of bottom bars. Strengthened beam means the beam with the double layer of 5T32 of bottom bars. The reason being of these two different calculations is to identify the reason why the design consultant had strengthened the bottom bars of the beam with the double layer of 5T32. The capacity concerned in this calculation is on the bending moment, shear force and deflection. Beam 2B.410 is chosen as example to represent all 23 numbers of beams. However, due to my level as an undergraduate student, simplifications on the calculation were made. The beam is considered as a simply supported beam with pin roller supports. Certain beams along grid line P to R 2 to 2.5 are ignored. Load transfer from slab along grid line P to R 2 to 2.5 is considered as all one-way slab. Column size considered as square columns. The height of flange of the flange beams is standardized as 275 mm at both sides. So the figure on the right shows the illustration of load transfer from slab to the secondary beams as well as the slab and the secondary beam to the primary beam 2B.410. So this is the detail of the beam 2B.410. Figure at the top shows the detail of beam before the modification work, which I labeled it as the non-strengthened beam. And figure at the bottom shows the detail of the beam that we received from the consultant for the modification work, which I labeled it as the strengthened beam. As it can be seen, the non-strengthened beam has 40-25 of bottom bars, while the strengthened beam has double layer of 50-32 of bottom bars. The shaded area is the depth of the beam that is to be reduced. The dark lines on the beam ends show the post-install rebar. These are the results from the calculations made. The applied moment and shear of beam 2B.410 are 832.94 kN meters and 244.7 kN respectively. The moment resistance for non-strengthened beam is 803.58 kN meters. Strengthened beam is 3115.93 kN meters. The shear resistance for non-strengthened beam is 1563.86 kN. Strengthened beam is 1515.17 kN. The deflection checks on the non-strengthened beam has failed due to the area of bars provided is less than the area of bars required, which had halted the calculation of actual L over D. The strengthened beam is 9.15 for the actual L over D, which is less than the 19.54 allowable L over D. The results show that the non-strengthened beam with 40-25 fails in bending moment and deflection due to it being lesser than the applied load. The strengthened beam with double layer of 50-32 passed in all three criteria. Although the strengthened beam, which is the actual modified beam with double layer of 50-32, CFRP is still provided, although the beam passes in shear strength. The reason being is because the calculation did not consider the hacking of concrete and concrete to concrete factor. Also, the shear links were damaged during the hacking process, in which it was not able to be replaced due to the construction ability. It is only able to be bent and fully welded. So due to this reason, it is considered that the shear strength of the beam is partially lost. Hence, a beam strengthening approach in the shear strength is required. It is proven in the literature review that CFRP increases 119% in shear strength with a fully U-wrap at maximum depth by vertical fiber alignment, in which this method is exactly the same method applied at the actual modification work as shown in the figure below. With this, it can be concluded that the strengthening in flexural by adding rebars and in shear by externally bonded CFRP, the modified beams pass in all three criteria. It is also learned that when a certain beam depth is reduced, a strengthening approach in flexural and shear strength are required. Due to the level 1 beam modification works, a new basement beam and column 1 beam is required to be constructed. The reason being is due to secondary beams that are highlighted in red and blue color have lost in its capacity, which require vertical restraint to reduce the moment in shear. The column arm beam is acting as a vertical restraint for the secondary beam highlighted in red color, while the new beam is acting as an additional restraint for the secondary beam highlighted in blue color, and to also transfer the load to the column on beam. Picture in the next slide will present a better explanation on this. With this vertical restraint, the secondary beam is no longer a simply supported but a continuous beam. Moment and shear within the beam will be transferred to the supports of the continuous beam, hence making the maximum moment and shear within the beam to be reduced. As it can be seen on the left side picture, the column on beam is provided to reduce the moment in shear of secondary beam A, which previously I highlighted in red color, while the new beam is to reduce the moment in shear for secondary beam B, which previously I highlighted in blue color. So the figure on the right is showing the drawing details for the basement beam, the level 1 column on beam, and the level 1 beam. The success of level 1 beam modification work has achieved the standard height clearance of the basement car park, which is 2.4 meters. So in finding out the height clearance, the formulas as shown here are being used. The level 1 structural finish level SFL is obtained from the concrete plan, while the basement floor finish level FFL is obtained from the architectural layout. Figures on the right show the concrete plan of level 1 and basement architectural layout, where the SFL and FFL are indicated in the red boxes. So the figure on the left side shows the cross-section view of the basement level, where the thickness of the slab and beam can be seen. With the beam depth that is measured from the top of the slab level to the bottom of the beam level, it makes the thickness of the slab to be neglected to calculate the height clearance of area beneath the beam. The results here show that areas that are not affected by the modified beam, the height clearance is already above the limit, which is 2.4 meters as stated by the architect. While for areas beneath the modified beams, the previous height clearance that is lower than 2.4 meters is now more than that. Figure on the right shows the overall picture of the concerned area with indicated height clearance in green, blue, and red boxes. The green box means the new height clearance. The red box means the previous height clearance, while the blue box means the unaffected height clearance. For the modification of RC structures where its capacity is concerning due to the major hacking works, temporary steel props are compulsory to be provided. Figure on the left shows the steel props characteristics as adopted from the technical material submission, while the figure on the right shows the design calculation of the temporary props. So it was found that 12 numbers of type M75 prop to be provided at every 4 meter squared area, which means 3 numbers of prop to be provided at every 2 meters apart. The figure on the left shows the location of the steel props that is to be placed. One blue dot represents 3 numbers of steel props. The steel props needs to be provided at both sides of the affected beam for balance of load distribution. However, although I found that the steel props needs to be provided with 3 numbers at every 2 meters apart, the actual numbers provided at the site is only 2 numbers at 2 meters apart, as shown in the figure on the right. This is probably due to the different manufacturer of the steel props that has a way higher strength provided by the subcontractor. Coming into the sustainability, in terms of environmental aspect, Sunway Construction had always been emphasizing for not just this beam modification work, but for all works on site. So the environmental aspect concerns of this beam modification work are the air quality, the noise level, waste management, and 5S. In controlling the air quality, the maintenance of machinery, which is the robotic hacking machine, is required to be done regularly. This is to control the soot and smoke emission from the robotic hacking machine. In terms of noise level, the modification works is ensured to be within the Department of Environmental (DOE) limit. The noise from the hacking works were controlled by minimizing unnecessary hacking works that will induce in unnecessary noise. In terms of waste management, a proper disposal of construction waste was carried out. All construction waste was disposed in the advisable manner as stated in the company SOP of construction waste management. The practice of 3R, reuse, reduce, and recycle, was also implemented at all times. One of the 3R's implementation was that all the demolished concrete debris was being reused as crusher run to maintain the logistic road within the construction site. The practice of 5S, which is sort, set in order, shine, standardize, and sustain, is also being implemented. It is always ensured that construction materials, tools, equipment, and machineries are properly stored in the designated storage area when they are not in use. Signage for hazards, storage area, and PIC are also being put up. Cleanliness of working area is always maintained to ensure a safe and healthy working environment. In terms of the economic sustainability, the modification work that is due to the design error had benefited different parties in developing their business. Both main and subcontractors as well as the suppliers are able to make profit in the business of construction works. The suppliers are able to make profit in supplying the materials, tools, equipments, and machineries. A total cost of about 385,000 ringgit was charged by the subcontractor to us as the main contractor. Then percentage of profit by Sunway Construction to charge the client is also being applied. The amount of profit gained by these contractors, the businesses of each contractor company is inarguably proved to be directly developed. In terms of social sustainability, due to working in a considered as a rare case of RC structure modification work, every personnel involved are naturally eager to have the hands-on experience together. Teamwork by not just the contractors but also the consultants has led to the success of this modification work. The mental health of all personnel involved is indirectly improved due to the positive working environment. The objective of this modification work that is to improve the functionality and practicality of basement car park area will deliver a better experience for the occupants in utilizing the area. The businesses developed had also positively impact the morale of the related parties. The client, consultant, contractor will have a better business image with the delivery of a quality building. So as for the conclusion, the beam modification work is a success in improving the functionality of the basement car park area. The standard allowable height clearance of 2.4 meters as advised by the architect was achieved with a proper construction design and methodology. Calculation and literature reviews had proven the original integrity of the affected structures to be maintained. The capacity in bending moment, shear force, and deflection of the affected beams have passed with the approach of beam strengthening. The need of beam strengthening in flexural by addition of rebars and shear strength by externally bonded CFRP are well explained. For my recommendations, the design consultants need to be more aware on the practicality and functionality factor when designing a building from scratch, rather than just a strong, safe, and aesthetic building. This may be achieved with the use of most advanced building design software or technology for 3D virtual reality design, as well as the architect as a lead design consultant in making a better coordination work process. So that is all about my presentation. Thank you and Assalamualaikum.